Good evening, everybody, and welcome to the public lecture. So I thought that I could give one line and say, ladies and gentlemen, tonight we have Sepp Dollmann, but maybe I need to say a few more things. And one of the things I need to say is that Sepp is the founding director of the Event Horizon Telescope project, and he is the person who led the international team that made the first image of a black hole. So I could stop also here, but I will continue. So he received his bachelor's from Reed College and a PhD in astrophysics from MIT. He was an assistant director of MIT's Haystacks Observatory, and then he received a Guggenheim Fellowship in 2012. And then he moved to Harvard Smithsonian Center for Astrophysics, where he co-founded Harvard's Black Hole Initiative. He's the recipient of the Lancelot M. Berkeley Prize and the Bruno Rossi Prize from the American Astronomical Society. And he has great plans for the future, which is to make movies. Unfortunately, movies of black holes. And we're looking forward to your talk. Thank you.
Okay. Thank you. It's a real pleasure to be here. Thank you, Petros, and to the organizers for inviting me. This is my first public talk in Switzerland, so it's a lovely venue, lovely place, and I understand this is a public talk, so this will be a little bit more general than a normal talk that I might give. I'm looking forward to all your questions afterwards as well. So the Event Horizon Telescope, simply put, is a project that we envisioned to make the first picture of a black hole. And the reason we wanted to do this was because the black hole represents the proving ground, the ultimate proving ground to test Einstein's theory of general relativity. It's here that gravity might break down. It's here that weaknesses in Einstein's theory might become evident. But more than that, black holes are terrifyingly efficient engines. They redistribute matter and energy on galactic scales. They change the way the night sky looks. So to understand what happens at the event horizon is also to understand the universe around us. So I want to start off, of course, by paying homage to Einstein, who grew up not far from here, and he completely redefined our notions of gravity. So if we're going to understand black holes, we need to understand where this idea came from. Now, he said that gravity is not necessarily action at a distance. It's not one body creating a force on another body and attracting them, but matter changes the shape of space-time, and other pieces of matter orbit in that deformed space-time, right? So you can see here, matter changes the shape of space-time and other matter moves around it. This immediately solved one of the most long-standing problems in gravity, which was the shift of the perihelion of Mercury. Mercury moves around the sun, and every time it gets close to the sun, it has a little kick, and it changes its orbit a little bit, just by a small amount, but Einstein's theory explained this. He also predicted that if you were to look close to the sun, light itself would be bent, that the apparent position of stars would be shifted during a solar eclipse. So when you could see stars very close to the limb of the sun, they would be bent by this amount, which is only about 1/2000th of a degree. A very, very small shift, but a very pronounced and clear one predicted by his theory. And he was right. In 1919, Sir Arthur Eddington sent 2 expeditions, one to Principe off the coast of Africa, and one to Brazil, and they captured this picture here, which shows the shift in the positions of stars exactly, or close to exactly, as Einstein predicted. And overnight he became a household name, lights all askew in the heavens, men of science more or less agog. You really had great headlines back then. And they said only a few people could really understand this. Maybe 12 wise men could really understand, wise people, could understand what was going on. Now, not long after this, during the period just after Einstein came with his theory, Schwarzschild, also with an amazing mustache, you had to have a mustache back then to really think of these theories, solved Einstein's equations. Now, Einstein didn't think there would be a closed solution so quickly. But Carl Schwarzschild said if you had just a point mass, he solved it in a very simple case, there would be a radius just outside this point mass called the event horizon, 2 times Newton's gravitational constant times the mass divided by c squared, where the force of gravity was so strong that even light couldn't escape. A one-way trip in, you could never get back out again. This was a mathematical curiosity for a long time. No one really thought that something like this could exist. In fact, Einstein thought it was abhorrent to his way of thinking that this could possibly exist. Nevertheless, astronomers began to see very strange objects in the sky, and it gave them the idea that maybe something like this really could exist. White dwarfs, for example, the end state of stars like our sun. They weigh as much as our sun, but they're only the size of the Earth, and they have a density of 1 million grams per centimeter cubed. Neutron stars were detected. This is something that with the mass of the sun, but the size of Basel. And the density here is 100 trillion grams per centimeter cubed. But even these are not black holes. Even these have a surface. Even these can be observed and understood. But there were inklings that if a star was much larger than our sun, and it died when its nuclear fuel was spent, and it could no longer resist the force of gravity, it could collapse into a single point, where it would only be defined by its mass and its spin, a black hole. But astronomers began to find things that were even more problematic. This is the Hercules A galaxy. It's many, billions of light years away. It weighs, a few billion times the mass of our sun, and everything you see here is optical light. You're looking at the combined light of trillions of stars. When you look at it in the radio, though, you see something very, very different. You see blowtorches of matter being directed over a scale of 1.5 million light years. This structure here is many times the size of the Milky Way galaxy. The amount of energy being distributed here is millions of supernovae, and it's directed from the north and south pole of what we assume is a spinning black hole. How does this happen? Accretion of hot plasma around the black hole starts spinning the black hole up. Magnetic fields are entrained in that hot plasma, which is billions of degrees. And then charged particles, as though they're stuck on a rotating wire, are flung centrifugally from the north and south poles of this object. This is how cosmic feedback works. These jets can stop star formation in its tracks. These jets can change the way galaxies look, and they can change the way galaxies nearby form. So this is fundamental to why our universe looks the way it does. So understanding this means getting up close and personal with what's happening right here. And the idea behind the Event Horizon Telescope was to do just that. Now, you might ask, how do black holes shine? Like, why are they able to shine? And the answer is that they are very, very efficient in turning gravitational potential energy into radiant light. So here you have an apple. If I were to drop it from this height, it would release 1 joule of energy. It would hit the ground. It would power your cell phone for about 1 second. If we were to take the Earth and scrunch it into the size of a marble, it would be a black hole. Same mass, just redistributing the space in which it resides. If you then drop the apple from the same height, by the time it reached the center, it would be going close to the speed of light. And you would be releasing 10 to the 16 joules, right? Many, many trillions times what this original apple was dropping. Now, this would power all of Manhattan, and not for 1 second, but for an entire year. This is the magic of black holes. Now, what does a black hole look like? Well, Max von Laue and others at the turn of the century, they knew that this event horizon, shown here in black with the same formula, was somehow the cause of some dark region that would swallow light close to the black hole. But it's really this last photon orbit which determines the size and shape of this black spot that defines the shadow of the black hole. And the way that Max von Laue and others did this is they started firing photons from our point of view towards the black hole, and they found the point at which they began to circulate around here forever. That provides the extent of the size of the shadow of the black hole. And you can see here they worked it out. It was the square root of 27 over 2. times that Schwarzschild radius. And I'm guaranteeing that your German is better than mine. But if you read this, then you'll see here, this is the square root of 27 over 2. So back in 1921, it was well understood the size and scale of what we were after when we were looking at the black hole. Now, this is what the black hole winds up looking like if you ray trace with a supercomputer all the light rays around the black hole. Towards our point of view, you wind up seeing this telltale feature here, which is the square root of 27 times the Schwarzschild radius. There's a lot of other tufty emission around there because the plasma is chaotic, it's roiling, it's bubbling. But over the course of many, many years, a number of people have used high-performance computing to work out, in the case of schematic or models or real general relativistic magnetohydrodynamic simulations, what this black hole should look like. And in all of these, you wind up seeing this circular feature. And if we could measure that, we could lay a ruler across space-time and weigh a black hole, simultaneously confirming Einstein's theory of gravity. Now, the best case for doing this is in our own Milky Way galaxy. It's in our own backyard. So the Milky Way galaxy is shown here in optical light, and if you zoom in by many, many factors, and you put on your radio goggles, the same ones that revealed that jet that I showed you before, you wind up seeing these streamers of ionized material falling in to the center of our galaxy. And this little dot here almost certainly marks the position of a 4 million solar mass black hole, one that weighs 4 million times what our sun does. Now, how do we know this? Because in the infrared, we have seen stars orbiting an unseen mass. This is incredible. You're seeing stars here orbiting something. They're being tossed around like they're planets. If this doesn't knock your socks off, your socks are on way too tight. I mean, this is really, when I first saw this was mind-blowing. And indeed, Andrea Ghez and Reinhard Genzel won the Nobel Prize a couple of years ago for this work. So we know that there's something here that is really mysterious. And how can we zoom in on that? The second object that we could hope to view the shadow of the black hole in is M87. And you can see here, this looks a little bit more like that standard jet source that I showed you before. The reason you only see one side of it here is because it's coming almost directly towards us, so it's Doppler boosted. The jet on the other side is still there. You can see it impacting the intergalactic medium, but it's deboosted. It's going away from us, so it's much fainter. When you zoom in by a factor of 10,000, you still just see this jet here, and this inner region here is unresolved. What exists here? Well, the best models that we have show that at long wavelengths, we can't pierce the hot gas that is surrounding the black hole. So we have to go to a wavelength of 1 millimeter. Then the whole environment becomes transparent, and we can see all the way to the event horizon. So we start with a long wavelength, and we go down to about 1 millimeter here, and then if we zoom in, you'll begin to see that ghostly trace of the event horizon, and you'll see what an active place it is. So this is gas orbiting around the black hole, brighter here because it's coming towards you, and fainter here because it's going away from us. Okay, so you want to build a telescope to see a black hole. We all want to do that. Since I was a kid, I wanted to do this, right? So you use the standard equation that astronomers do. The smallest size you can see on the sky is equivalent to the wavelength of light you're observing, in our case radio waves, divided by the size of the telescope. Now, we're after things that are only 50 micro arc seconds across. That's equivalent to seeing an orange on the moon. Or if you held an atom at arm's length, you could see that atom. This is the highest angular resolution we've ever attempted to produce from the surface of our planet. But as I said before, we have to see through all of the hot gas near the black hole, but also our own atmosphere and gas between us and the center of the galaxy. So once we fix this as being 1 millimeter, then we need a 10,000 kilometer dish. Now, of course, we can't build a 10,000 kilometer dish. These are standard dishes, radio dishes. This is in Australia, and this shows that this parabolic surface, this perfect parabolic surface, is tuned to take a plane wave from radiation from the black hole, bounce it to the focus where everything is combined perfectly, and that's where you put your camera. So this uses geometry to focus all these radio waves and combine them together. And of course, we can't build a telescope that's the size of our Earth. So we found a way to get around this. We use something called very long baseline interferometry. We essentially take this dish and we smack it with a hammer. And we take the shards of this dish and we put it all over the surface of the Earth. And then we operate them as independent dishes, assuming that we can take all the data that we've seen from them and combine them later. So we start with radio telescopes at different sides of the Earth. We digitize all the radio waves that are coming from this black hole, and we time tag them with hydrogen clocks, hydrogen maser clocks. These are atomic clocks that are so accurate they only lose 1 second every 10 million years. So every trough, every crest of the radio waves are time tagged perfectly so they can be synchronized at a later time. They're stored on hard disk drives, the same ones that you use in your computers, ones and zeros. We essentially freeze the light on these hard disk drives, and we take them to a correlator, which is just a supercomputer that combines them. So we reproduce the perfect shape of the parabola of the dish in silicon, and we run the streams from these two dishes by each other until they perfectly align. We combine them, and each individual pair of telescopes gives us one bit of information about the image. So think about that. Every pair of telescopes is almost equivalent to 1 pixel in this Earth-sized virtual array. For those of you who care to know, each pair of telescopes selects 1 Fourier component of the brightness distribution on the sky. Now, if we only had a few dishes around the globe, we would never be able to make an image. We wouldn't have enough Fourier spatial frequencies, enough pixels to do that. Thankfully, for a number of different reasons, the Earth rotates, and with different look directions, we wind up getting many, many different baseline pairs during the course of an evening, and you fill in this virtual Earth-sized telescope. You can see all the little red dots dancing around here. And if the source is stationary, if it's not moving too much, you can combine all the data from an evening to make one image. Now, when we first had this idea, we had to ground ourselves in reality. Was there a structure to be seen? If we looked at the galactic center, Sagittarius A star and the Milky Way, was there something to see? And the answer was yes. Over a course of about a decade, we ran experiments between Hawaii and California and Arizona, looking at the center of our galaxy. Now, what would we hope to see? Let's say that Sagittarius A star was this big. Okay, this is the brightness distribution on the sky. This short baseline here, lambda over d, the wavelength divided by the distance, is fairly large. So we'd expect to absorb all of the light from Sagittarius A star. But on the long baselines, lambda over d gets small. So we wind up having a smaller region on the sky that we're sensitive to. We would expect to exclude some of the brightness. And this is exactly what we saw. This is energy on this axis, baseline length on this axis. On the short baselines between Arizona and California, we detected all of the flux density, all of the radiant light from Sagittarius A star. But on the long baselines, as expected for a source of a finite size, we excluded that flux and saw something greatly diminished. The size we infer from this is about 4 Schwarzschild radii. So now we knew that there was something to see, because the shadow itself should be about 5 Schwarzschild radii. So now we knew we could see all the way through the hot gas to the event horizon, and we simply had to build out the array to take an image. So we did this in April of 2017, and you can see here all the different sites around the globe that we were able to convince. It took a little convincing. We were able to convince them to do these observations. So the SMT in Arizona, the LMT in Mexico, 2 telescopes, the SMA and JCMT in Hawaii, 2 telescopes, ALMA and APEX in Chile. The South Pole came along for the ride. And providing a very important outrigger here in Europe was the IRAM 30 meter in Andalusia in southern Spain. Now, before I get into this right here, I just want to say that this worked beyond all of our expectations. After years of preparation, all of the sites worked. All of the data was collected. All the data made it back without getting lost in the mail. It all came back to the central facility, and we were all able to write these papers and make the first image of a black hole. But I wanted to show you the journey that some of these photons frozen in hard disk drives took from the South Pole. So this is Andrew at the South Pole packing up banks and banks of hard disk drives. They back up here in a FedEx truck. This is light being delivered by FedEx. We unload the disk with a forklift. Apparently, you can maneuver light with a forklift. We unpack it, and here they are defrosting from their long trip from the South Pole. This is about a petabyte of data right here. Now, this is nothing new. It turns out we're not the only people, or the first people to think about unloading large amounts of data. In 1956, if you wanted 5 megabytes of storage, you could get it from IBM, and they'd come and deliver it with these strong guys, and they would bring it right to your lab. So some things remain the same, but of course, the scale of the storage is much, much different now. So when we first got the data, we were very excited. That might be the understatement of our careers. Because when we looked at this same plot that I showed you before, energy on this axis, baseline length on this axis, we could see right away there were some interesting signatures, these bounces, in the Fourier domain, or in the domain of these baseline pairs. If you tried to model this with just a blob, or what we call a Gaussian, you would never be able to recreate this same structure. If you start looking at something with a hard circular edge, the Fourier transform of this starts giving you these bounces, but they're in the wrong place. It's when you start to look at rings that these nulls start to match the data. But still, it's not a very good fit yet. And it's when you look at a crescent with one side brighter than the other that you get families of curves that can immediately produce this. So my postdocs came to me with this data during a dinner we were having. And there are pictures of us just with our mouths open at dinner, looking at this data for the first time. And I went to my office afterwards, and I calculated the diameter of this ring based on this, and it was clear that we had something very, very interesting. So now we have to make images, and I'm not going to go too much into detail on this, but suffice to say that making images when you don't have all of your pixels is quite an interesting problem. So every place you see here that's filled with color is where we have data, but you have large holes here where we don't have data. So we have to use a combination of looking at data and also regularizers. We enforce the condition that the distribution is smooth, right? We enforce the condition that the brightness on the sky has to be real and not imaginary or with crazy values. But we use relatively benign regularizers here. And you can see the process iteratively of going to these data, changing our model, going back to the data, changing our model, looking at the regularizers, and over time, you gradually converge on something that looks like this, a ring. Now, this is early simulation data. This is not the actual data that we used. So we split ourselves up into 4 teams. We did this because we had never imaged a black hole before. Nobody had ever imaged a black hole before. And so we thought, let's not fool ourselves. Let's treat each team completely independently. Each team used different diagnostics, different methods, different approaches, and they didn't talk to each other. We put a clear boundary on any distribution between the teams. And again, the reason for this is that it's really hard to tell the difference between fried chicken and labradoodles. Okay? You can be convinced that you're looking at a piece of fried chicken until it begins to bark. And then you realize, I've actually been looking at a labradoodle this whole time. And it gets worse when you have everybody around you thinking like, I think that's a piece of chicken, and then it starts barking. And if you think that's hard, Chihuahuas and English muffins are virtually indistinguishable. So it all came down to one moment on July 24th in 2018, and all 4 teams came together at the Black Hole Initiative at Harvard University, and every team from all over the globe were seeing this ring-like feature. So now we knew that not only did we see it in the data, but also with all of our methods, we were finding the same kind of structure. And this is where we are. So this is many of us here in the basement of the Black Hole Initiative. This is what I call a beer moment. This is not a champagne moment, because even though we were pretty convinced that we knew what we had, we spent 6 more months after this trying to make it go away. And this is what science is about, right? You find something, but if you're going to come with a great result, you have to have great confidence in it. So we spent 6 months trying to make this go away. So we would train all of our methods on different morphologies. Could they be reproduced with a double source? Could it be a filled disk? Could it be a ring that was uniform? And we would train our methods on structure that was not the ring. And once they were fully trained, and that's what they knew how to produce, we would turn them loose on the real data, and they still produced rings. Okay, this is when we started to understand that it was a very, very robust result. Also, we looked at other objects. This is the Quasar 3C279, which we expected would have the same kind of core jet morphology that I showed you all the way at the beginning of the talk. And indeed, here, we saw the bright core and the jet going off in the direction that we expected with all of the different methods that we used. In addition to this, we also had 4 separate days of data, completely independently produced and recorded at different times, at different days. So April 5th, 6th, 10th, and 11th, every single day gave us the same ring, the same diameter, the same structure. Now, it's very important that we had as many sites as we did. If we had had, I think, 1 fewer site, we would not have been able to come with this result. Right? So here you see what you can say when you only have 2 stations, baseline here in Arizona and in Mexico. You can only tell roughly what the size is. In the whole Earth-sized aperture, we only have these 2 points. It's when you start adding longer baselines, well, now you can tell that there's something smaller there, but you can't really see the ring yet, because we don't have enough of our Fourier spatial frequencies. We don't have enough of the virtual pixels filled in. When you add Hawaii in this outrigger configuration, now you begin to see the hint of the ring, because now you have different look directions towards the black hole. And it's when you add all of the sites, with Spain, Hawaii, and everything in between, this is when you get the full result. So as with real estate, in very long baseline interferometry, it's location, location, location. Right? You really need to get all the sites in order to come with this result. Now, what did we measure? Well, there are many, many different ways of doing this. You can fit models to the data. You can fit simulations to the data even. And I'm going to show you one technique here, which is where you've traced the ridge line of many, many images that you make over all the days and all the times. And you're able to look at the width of the ring, shown here on the bottom, and the radius as a function of azimuth angle around here. And what we're trying to do, quite simply, is solve this equation. We know what the angular diameter of the shadow is. And remember, we're looking at angles here. We don't know exactly how big this black hole is, but we're measuring an angle on the sky, so many microseconds. And that has to be the square root of 27 here. This is the same term that we learned about before. Newton's gravitational constant, the mass of the black hole, c squared, the speed of light squared. And because there's an angular diameter, we have the distance to the black hole. So if we know the distance, if we measure this shadow diameter, we'll be able to read off the mass. And this is what we did. We know the distance fairly well because we can see oscillating stars in this far-off galaxy, like Cepheids and other methods. And we measured the mass of this black hole to be 6.5 billion times the mass of our sun. Okay, let's just appreciate this for a moment. There are 6.5 billion suns inside the photon orbit. This is the orbit that light makes around a mass that big if it's focused in the center. There's nowhere for the black hole to hide anymore. This can only be a black hole. Right? There's nothing else that could do this. There are a couple of exotic possibilities that have never been observed in nature. This is the best evidence for the existence of supermassive black holes ever yet produced by humans. There's probably a very smart civilization somewhere else that has done this too. But this really is the best evidence that we have for the existence of these kinds of monsters. So from this particular image, we see the following. We get this mass from general relativity, so we've used Einstein's theories to measure the mass and simultaneously confirmed one of the singular predictions of Einstein's theory, that you would see this shadow. It's circular to within about 10%, which is exactly what we predicted for this jet, which, as I said before, is coming directly to us. And it's asymmetric. You can see here there's brightness on the bottom and dim at the top, and as I mentioned before, that's because gas is circulating around the black hole. It's coming towards us at the bottom, going away from us at the top, and this allows us to measure the orientation of the spin. So if you take your hand, and for those of you who know the right-hand rule, then you put your thumb in the direction of the spin slightly into the page, and your fingers will naturally curve up from below. And that's the direction of the flow of the hypervelocity gas around the black hole. Brighter on the bottom and dimmer on the top. So it's consistent with Einstein's theory at the 17% level, and we're going to do a lot better in the future. I mean, this is just our first foray, and we're going to build out the array, and I'll tell you how we're going to do that in a moment. So we're going to improve these measurements all the time. But it also allows us to study the details of the flow around the black hole. Because remember, we got into this not just because we wanted to test Einstein's theory, but also because we wanted to understand the accretion flow, how black holes eat, how they launch these jets. So we used, and this is maybe perhaps why I'm here, high-performance supercomputing to do this, and we used general relativistic magnetohydrodynamic simulations, and we ran hundreds of thousands of them, all tested against the data. And from these, we were able to limit the temperature profile of the gas, the magnetic fields in the gas, the spin of the black hole. We've learned more about the environment just outside the event horizon from these measurements than we have before. Somewhat seizure-inducing, sorry about that. But it's quite interesting to see. And this was all made possible by a number of different universities around the entire globe. Now, what about Sagittarius A star? I've shown you everything about M87, and you might ask, where is the center of our galaxy? Because we're all basically selfish people about this stuff. So one of the problems with the Sagittarius A star is that we are in a spiral galaxy. So we are in the plane of the galaxy. So when we look all the way to the center of the galaxy, it's through ionized gas, and a lot of it. And that blurs the image that we try to make, especially at longer wavelengths, because we're scattering off of free electrons. Because all the gas is ionized, the electrons are off of their atoms. So for a wavelength of 3 millimeters here, you would normally see this kind of structure, but theoretically, this is what we would see. The scattering completely destroys any evidence of the shadow. For at 1.3 millimeters, what we observed with the Event Horizon Telescope, the situation is bad, but you can still see the shape and size of that shadow. And when you get to 0.8 millimeters, where we hope to go by next year, you can still see all of the details. So Sagittarius A star presented a difficult challenge for us. How do we handle the scattering? How do we extract the shadow? There was another problem. M87 is so big that the time it takes light to orbit around it is weeks. So it stays motionless, essentially in the sky during a night of observing. So we can take all the data we recorded at night and make a still image. But for Sagittarius A star, the orbital period of matter is about half an hour. The orbital period of matter is about half an hour. So it changes its appearance many times during the night. So you really have to make a movie or an average image. So we had to retool all of our algorithms to handle these two new challenges. And this is what we came up with. We definitely see a ring. We are not going to guarantee the azimuthal structure around the ring, but we do stand by the robust size of this ring. And of course, as we get many more telescopes, we'll be able to make movies of this black hole and get the diameter and the space-time geometry much better. So the mass from the stellar orbits that I showed you before is 4 million solar masses, and the size of this ring is exactly what you would predict from that mass. And now we have two sources, so this corroborates what we did with M87, and this, as I said, is the best evidence for the existence of supermassive black holes. I want to pause here for a minute and point out that the important thing is that black holes are the same no matter what size they are. When a star dies and the black hole is 10 solar masses, it is governed by the mass, the charge, and the spin. When you have M87, which is 6.5 billion solar masses, it is also governed by the mass, charge, and spin. They're identical. and they should obey all the same laws of Einstein's physics and gravity. And this is what we wind up seeing. This is incredible. For example, if you took a mouse and you scaled a mouse up by 1 billion, it wouldn't be a mouse anymore, right? It would just be like a steaming pile of mouse. You know? I mean, it couldn't support itself. All of its bones would break. The heart couldn't pump. All the laws that govern the mouse would be completely different for something that was 1 billion times that size. This is not the same thing for black holes. A black hole that is 1 billion times more massive than another one is exactly the same, and it obeys the same laws of physics. So what are we doing next? So now we want to take this array that we have right now, shown here in blue, and we want to build it out so we can make movies of black holes, as Petros said. This is also our secret plan for world domination, but we're not really going to go into that right now. So we've looked at all of these sites, all of which are high elevation sites, because we want to be above the water vapor, because water vapor does absorb the radio waves at this wavelength that we're detecting. And when you wind up doing that, you can take this UV coverage, or this Fourier coverage, this Earth-sized virtual array coverage that we have right now, and when we add, let's say, 5 new dishes, and we go higher in frequency, we start filling in this Earth-sized virtual lens, and we add 10 new sites incorporating Africa now, and new sites in South America, and more in Europe here, we get near total coverage. This is what's going to allow us to make dynamic range images of 1,000 to 1. This is what will allow us to make movies from moment to moment, trace the dynamics of black holes in motion. So here's an example. One of the things that we'd like to study is how the black hole launches these jets. Now, the careful observer would have noted that I've shown you a couple of these jets, but for M87, all we see is the black hole. Where's the jet? Where is the jet that we know exists on larger scales and that we know has to be launched by this black hole? The answer is we don't have the dynamic range currently to map this very faint structure here. So this is a simulation, and this is what we would be able to image with the next generation EHT with 10 more sites. But it gets better, because what we're really after are the dynamics. We'll be able to take this simulated movie, which shows the flow of energy, both in particles and pointing flux, the electromagnetic fields that flow through the jet, and we'll be able to trace them with great fidelity as a function of time. And we'll do this by looking at M87 every week, a couple of times, and stitching all these frames together to make a time-lapse movie of a black hole in action. For Sagittarius A star, we'll be able to take moment-by-moment snapshots. So this is a model which shows the evolution in time of the black hole, very close to what we would expect for Sagittarius A star. And for the next generation EHT, we'll be able to trace some of the dynamics as matter flows around this black hole as a function of time. And this is important, because everything I've showed you so far has to do with light bending around the black hole. The very shadow is caused because light is in the field of gravity of the black hole. What you're seeing here is luminous matter, which can't move at the speed of light, orbiting the black hole. This is a completely different test of Einstein's theory of gravity. And why should we be limited to the Earth? If we were able to launch satellites that orbited the Earth in low Earth orbit, we would be able to fill in that Earth-sized virtual lens in minutes, maybe hours. And we could make real high-fidelity movies of Sagittarius A star. And what's more, imagine we've launched a telescope into the second Lagrange point, which is 1.5 million kilometers from Earth. Every black hole that we know of would then come into range. We would have the angular resolution of sub-micro arc seconds, and we could see black holes across all of cosmic time. And we'd be able to do demographics of black holes, study them in the aggregate, looking at populations as a function of time, and see them in great detail. There's a lot that's going on. Both of these different missions are being considered right now and are being proposed. So here's the model, here's what we hope to do from the Earth, and this is what we hope to do from space with a geosynchronous orbiting satellite. So this all happens because we have a team. As the proverb goes, if you want to go fast, go alone. And in the beginning, we did go very, very fast, and we went alone. But if you want to build an Earth-sized telescope, you need an Earth-sized team. And this is all of us together in 2019, right before COVID. Yuck. But we were all unmasked and having a good time here in the big island of Hawaii. And this is a remarkable group. It's been the privilege of a lifetime to work with all of these people. At the time, we had 200 members, 60 institutes, 20 countries and regions represented. Now it's well over 300. And I will point out to the young people in this audience that the early career people in this project made substantial contributions. But I would go so far as to say that without the early career researchers, the students and the postdocs, this would not have happened. They came with creativity, they came with dedication, and they came with a resilience that was a marvel. And without them, we simply would not have been able to see this through. There's a human dimension to this. We came down from our hotel rooms after the press conference when we announced this, and we were frankly stunned that the front page of every major newspaper around the globe were showing this. Now, why is this? In truth, I still don't quite get it. I think it's a mixture of things. I think it's that black holes have been like dragons. They were mythical. They were mythical beasts, and we could imbue them with almost any quality that we could consider. They were the subjects of movies, of science fiction stories, and they were something that, as long as we didn't see it, could be anything we wanted it to. And now that we saw it for the first time, there was something very real about it. Dragons did exist. Black holes do exist. The other thing is that we did it as a team. We were able to reach across borders, nimbly sidestepping all of the issues that tend to divide us as people. And we came together drawing on not just expertise from around the globe, but we turned the Earth itself into a telescope. No one country could have done this by itself. And this was an amazing challenge. The very idea of a black hole is something that swallows light. And here we were imaging it. It's hard to wrap your brain around that, but it was a seemingly impossible problem that we solved together. And I think all of this resonated with the average person. So I would get into cabs, for example, and the cab driver was, right after this, and the cab driver would say, "Hey, did you hear about that black hole?" And I would say, "No, tell me about that." And he would get so upset with me that I was a slow learner. He's like, "Well, they had different telescopes, baselines, come on, you know." But it was such a treat to see people engage with not just the wonder of it, but also with the mechanics of it. So I just wanted to end up by saying, what would Einstein think? I really wish that Einstein were here. I really wish that Stephen Hawking were here. Sadly, Stephen passed just a couple of years before we came with this result. I met him, I talked with him about this, he understood what we were up to, and I was really hoping that he would be around to see these two images. But Einstein was a big proponent of this kind of work. He pushed for this observation that tested his theories. He would have loved the fact that we were putting his theories again to the test, right at the point where his theories might break down. He would have loved it. But I also think sometimes about going back in time and talking to Einstein. I'm sure we all have our heroes that we want to go back in time and talk to. And this gets back to the idea of basic research informing our lives. So right now we use GPS. And unless you use Einstein's equations, GPS will be off by miles. Okay, you need general relativity for GPS to work. So imagine going back and talking to Einstein. You'd say, "Here, Professor Einstein, 100 years from now, I know you don't know this, but 100 years from now, we'll take your theory of general relativity, and you'll be able to, using your phone, tell where you are anywhere on the Earth using a constellation of satellites." He would be so tickled. He'd be very excited. He would say, "What's a phone?" You know, I mean, that's how far we've come, right? I mean, we're using technology that he could never even conceived of. Sometimes you have to wait a long time for basic science to pay off, but it's always a good bet. And this has been the thrill of a lifetime. Thank you very much.
Okay, I will not come near you. I will start from here, the questions. No. So, any questions from the audience? Please.
So thanks a lot for this talk. I have seen parts of this from Luciano Rezzolla in Frankfurt, a colleague of mine. And I saw his simulation of the two neutron stars encircling each other, doing the gravitation waves, and then as a complete outsider to the topic, I was completely amazed that the rotation of those neutron stars are in milliseconds. Now you're showing those movies, and we have a spatial scale that you said, and I was wondering about the temporal scale. So how long are those movies? And if you say that you want to make movies by doing those telescopes together, is it just incredible luck that you are getting a time scale where something interesting is happening, where you do not have to wait billion years until something moves, or it's in the picoseconds where you can't measure it or something? And what do you expect at very small and very long time scales?
It's a great question. It's a great question. So first of all, I remember somebody told me once they had a rugby coach, and the rugby coach said, it's better to be lucky than to be good. Okay, now, I don't subscribe to that, but luck does play a bit of a role here. So I'll answer your first question, which is the time scale on these movies is commensurate or the same as the time it takes matter to orbit around the black hole. So black holes are very strange. They deform space-time. So there's something called an innermost stable circular orbit. There's an orbit that's close to the black hole, and if you go further in, you spiral into the black hole. You can't escape. Okay? That's not the same as the Earth, right? You could potentially have a satellite skimming the Earth, and it would be able to go all the way around if there was no atmosphere. You can get as close as you want to in Newtonian dynamics to a mass, and the centrifugal force will keep you moving along, and you go faster and faster. When the skater pulls their arms in, they spin faster and faster. The problem with the black hole is that the speed of light is a limit. So you can't keep going faster and faster. So at some point, you just fall into the black hole. So the size and the time scale of those movies is minutes for Sagittarius A star, and for M87, it's weeks. Okay, so essentially every minute for around Sag A star equates to a day around M87. Now, on the luck part, think about an eclipse. We're able to see the corona of the sun because the angular size of the moon fits just around the sun. And the distance of the Earth from both of those is just perfect so that we can see the corona, see the distortion predicted by Einstein of the positions of stars. That's crazy. Like if it was just 1% different, you'd never see this, right? And here we have a case where these black holes are just the right mass at just the right distance. The wavelength of light goes through our atmosphere, goes all the way through the hot gas near the black hole, and that lambda over d for the size of our planet is just enough to make these images. I mean, you can't make this up, and I don't know who thought of it, but I'm just the happy beneficiary of it.
Please.
You clearly found that the best way to get the data back from Antarctica was over land rather than by satellite, say. So with this idea of putting a satellite at a Lagrange point, what complications do you envisage in getting the data back from such a long distance?
Yeah, that's a great question. So it turns out that there are a few things that trouble us about doing this in space. The first is the time standard. How do you launch an atomic clock into space? How do you guarantee it's going to be of the right stability? Another one is getting a big enough dish in space. It's easy to put a large dish on the surface of the Earth, much harder to get one into space. And the third point is what you brought up. When you're recording 256 gigabits per second, how do you get all that back from L2? Because the power of the laser it would take to beam all that data back is going to be huge, right? So how do you do that? We're thinking about recording in bursts, for example, storing things on solid-state drives on the spacecraft and then bleeding it back over long periods of time. Because if you're all the way out in L2, you're moving very slowly. So you might be able to record a little bit of data, send it back, and then when the spacecraft has moved a while, take more data, and then more data. So there are ways in which we might be able to recover all of the data we need without necessarily overtaxing the system that brings the data back. But this is still a very open area of investigation.
Please.
Just before, you mentioned that during the study for M87, you considered the magnetic field. So I remember that a few time ago, another paper was published about the NICER observation of three polar magnetic field. So I was wondering if considering a more exotic magnetic field could in some way change the observation or the data that you are seeing, let's say.
Okay, I didn't understand the specific magnetic field you were talking about.
In the NICER group, I saw a paper, public paper, let's say, not scientific, mentioning the fact that the NICER collaboration, there was they saw a three-polar magnetic field, so a magnetic field with three poles.
Ah, okay. Well, so I'm not familiar specifically with what you're talking about, but what I will say is that we are ranging all these simulations over a big parameter space. So we're not necessarily locking ourselves into any one thing. This is the opportunity to look for the unexpected. Right? This is the opportunity to see things that we haven't imagined before. If we locked ourselves into one topology of the magnetic field, poloidal or toroidal, we would be doing a huge disservice to everyone that took these data, right? Now is the moment to be expansive. Now is the moment to be capacious in the kind of ideas that we're considering. They also lead us in different directions. So if we have different magnetic field topologies, different geometries, they make specific predictions. And as we think about building out the new array, where we place these dishes will be informed by the kind of science we want to do. We do not want to put dishes in places that will foreclose the kind of science we could do in the future. So these kinds of questions, asking ourselves to be very general, are very important.
Other questions?
I think there's one over here.
Oh, I'm sorry. Please.
I actually have two, one technical and one non-technical. And I'm not sure if my answer to the first one might have been embedded in an earlier answer that you gave, but I wasn't clear on why the shadow is larger than the event horizon. And then the second question is, one of the things I find really exciting about your work is that you have a very clear and strong motivation to span the globe because you need this long baseline. And so I came to this talk from a session on diversity, equity, and inclusion, and I can't help but wonder to what extent there was an effort and maybe even a requirement by the governments to involve scholars in some of these far-flung places.
Yeah, well, first of all, very excellent question. So let me address because I forgot the first one, I'll address the second one first.
Okay.
What was the first one again?
Why is the shadow bigger than the event horizon?
Oh, yeah, okay. That's a good one. So let's start with that. So the first one of the first slides I showed, you see the impact parameter, right? So you see if you fire light rays towards the black hole, and here's the event horizon, they kind of curve in like this. So the impact parameter, or the size of the shadow, is going to be bigger than the event horizon itself because something that's outside of the event horizon curves in to impact it, right? So the size of this is magnified just by the fact that the space-time is deformed around the event horizon. So that's why it's like the mirrors that you see that say objects in the mirror are closer than they appear, right? It's because there's a deformation in the space-time. On the equity and inclusion, it's extremely important, especially as we think about new sites in, let's say, Africa or in South America. That we have a special duty and an obligation, and really a privilege to involve people from all over the globe in this. And we would be doing ourselves a big disservice if we didn't. I mean, there are a lot of studies that show that through diversity, your science always gets better. And that's what we want to do as we go to these new places. It's also important because we'll be going to remote sites. It turns out that we have to be on mountaintops. It turns out that we have to be in remote areas. And we have to work very carefully with local populations, bringing them in for considerations of economics, education, opportunities for work, but also different ways of knowing. This is only going to happen if we bring our cosmologies having to do with black holes and we have conversations about other cosmologies. I view this as a real opportunity to broaden everyone's horizons as we think about the universe.
Please.
Thank you very much for this very inspiring talk. So I also have two questions. The first one is related to, you said that you plan to expand to include 5 more radio telescopes and then 10 and so on. What is the improvement that you would get, not on the side of the movies, but on this particular signal to noise ratio that you have, with including already 1 or 2 more? And do you already have the setup to do that, or is 5 the bare minimum? And the second one is related to the algorithms that you had to develop in order to see these nice images. I know that a lot of AI was involved. Are they public, and how do you see that other fields can profit from what you've developed in order to get this,
Yeah, it's a great question. So first, you have to remind me of the second one because my short-term memory is gone. But the first one was, 1 or 2 telescopes, yeah. That's embarrassing. So it turns out that when you add 1 telescope to the array, it's very difficult. I mean, imagine you go to a funding agency. You go to the National Science Foundation or the ERC, and you say, I've got 10 telescopes, 1 more is really going to do it. It's a very difficult argument to make. So what we do is we always look to the next big transformational shift, 5 telescopes or 10 telescopes. And then we retrench and we find out how we're going to individually get those 5 telescopes. We work with people around the globe. This is not a European project. This is not a US project. It's not a South American project. It's not an African project. This is a global project. So we only succeed if everyone is being lifted together by this coherent scientific vision. Now, that said, the first detections we made back in 2008 involved 3 antennas. You can do a lot with 3 antennas. You can make a career out of 3 antennas. And that's what we've done. What we gain from multiple antennas is the following. Not just you don't increase the SNR alone, although you do, and you don't increase your angular resolution as you go to higher frequency with more antennas, which you do, but also sometimes it snows. Have you guys noticed that? Did you hear the hailstorm that happened just a couple of nights ago? Like hail in June? So when you have more telescopes, you're more resilient to weather closures. So we sit in what we call the Array Operations Center every time we do these observations. And we're pulling our hair out, right? Because it'll be great weather in Chile, and it's snowing in Spain. So we don't have the whole array, right? Or it'll be great weather in Spain, and all of a sudden Hawaii is iced over, right? When you have many, many more sites, you become resilient to that. You have contingency. So you might not have all the sites, but you have enough at any given moment to make the image you want to make a time-lapse movie, for example. So even having a couple of new sites can help us on that score. The other thing is that this image that you see, these images here, I didn't get a chance to go into this because this is not a formal colloquium, but these themselves can be decomposed into the light that is gently bent around the black hole, and then light that makes a U-turn around the black hole, which is represented by a much thinner ring. And then there's light that does a complete orbit around the black hole, which is thinner yet. Each of these thin rings gets us closer to Einstein's gravity. So when you add more dishes at a higher frequency, we'll be able to decompose this and make tests of Einstein's gravity that are at the 1% level, not at the 17% level. So it all helps. And now I've forgotten the second part of your question.
Open source algorithms.
Yeah, the open source, yeah, everything is open source. Everything, so when we publish our papers, we not only publish all the data, but all the code and all the routines and all the harness, like the software harnesses, it's all published. It's all open source. And as a matter of fact, what's really nice about this is that I think 3 or 4 groups have independently taken these data and have corroborated all of these results. Oh, how will it be used? Well, so for example, if I met somebody here before who was doing exoplanets, I forget where they are. Marco, was it? There he is, Marco. So Marco is also an astronomer, and he does exoplanets. And these exact same algorithms are being used for, not exoplanets, but protoplanets, like planetary formation, right? Yeah. So we're using these now for looking at the formation of planets, and there are some arrays that can see protoplanetary systems, and they look not unlike this, with rings. And planets form in these rings of material around stars, and we've used these same methods for that as an example.
Other question? Please.
Thank you very much for the very interesting talk. It's very amazing that you have actually confirmed the most extreme case of general relativity that you observed. I'm just wondering that you now already studying the next generation of the observation, if there is any aspect of this observation where you think new physics can hide.
Yeah, that's a great question. So it turns out that at the moment, everything looks as though this is the Kerr geometry, a spinning black hole geometry. But we've devised tests now to look for outlier cases where you could have a different form of gravity. You could have a non-Kerr geometry. And there are predictions that would cause these particular black holes to be ellipsoidal, for example, or to change in shape. And these tests can be much more precise with more telescopes as we add them to the array. So we're always thinking about ways to test Einstein's theory with even more robustness. And secretly, not a secret, but secretly, it'd be so cool if we could find something that was unexpected, right? So we're always on the look for something like that. So far, we haven't seen it. There are also some pathological cases. There are boson stars that could mimic what a black hole looks like, but actually has a surface. And so we're just starting to rule those out. Imagine you had an object whose surface was just outside the event horizon. So it was not really a black hole. It turns out that some of the material raining on that surface would begin to heat and glow. And we're at the point now where we can rule some of these out because we don't see that glowing surface. We don't see the telltale infrared spectrum from that hot surface that we might expect to see. So we are absolutely looking at different black hole constructs, exotic black hole mimickers is what we call it, but also different gravities.
Is it possible to get three-dimensional images of the black holes? Could we ever have something like that? Is it of interest at all? I don't know.
Well, my first impression is that we'd have to make a deal with somebody on the other side of the galaxy.
Or with the satellites or the things that you send out there, I don't know.
Yeah. Where are the aliens when you need them? The traditional way of doing this, Petros, is you find a spectral signature. So for example, when you're looking at a molecular line that's been excited in an astrophysical context, the velocity of those molecules is encoded in the Doppler shift, right? So looking at different frequencies, you make different maps, and you can, like an MRI, you can take slices through a nebula. You can take slices through a protoplanetary disk and tease out the 3 dimensions. This is continuum emission, right? This is synchrotron emission. It's charged particles orbiting magnetic fields, giving off a broad spectrum of emission, so it's much more difficult to do that here. We might be able to do what you're talking about through modeling, though, because we do have very sophisticated general relativistic models, and if we get enough information with time, and we can model the rotational structure, we might be able to infer the 3-dimensional rotational structure around the black hole. That's what I think we'll do.
Okay, thank you. Is there a last question? Last question, please.
Yes. With the Webb telescope, we now know that it's possible to put satellites 1 million kilometers away from the Earth.
Where are you?
Here.
Okay.
Sorry. But what about the moon? Is it of any interest at all to put a dish on the moon?
Who doesn't want to go to the moon? I mean, honestly, I'd love to go to the moon. So the moon is great. The moon is closer than L2, so the moon is much closer than the second Lagrange point, which is 1.5 million kilometers away. On the moon, you could put a much larger dish because you could ostensibly build it with local materials perhaps, or land something on the moon and people could build it. But there's certainly possibilities on the moon. And once you get beyond a certain point, the angular resolution of the Earth to the moon distance brings all of the black holes you might ever hope to observe into range, right? So you can look at any shadow across cosmic time with the moon-Earth baseline. The problem, though, is that things do get faint, and you've got to get the data back, and you have to build a pretty large dish on the moon in order to make this work. But that's certainly a possibility.
Okay, I'd like to suggest that we thank Shep very much for a fantastic talk. Thank you. That was fantastic.